Welcome to the second video in the series of acid and base videos. This one's on pH calculations and corresponds to part of the specification reference 3.4.3. So in this video lesson, let's go over the learning objectives. First one being that we need to know that pH equals the minus log to the base 10 of the hydrogen ion concentration. We also need to know its inverse as well, which we'll cover off. Then we're going to convert concentrations into pH and pH into concentrations. That's concentrations of either acids or bases. And then we're going to be able to calculate the pH of a strong acid from its concentration, and likewise the same for a strong base. The base being slightly more complicated in that we also need to use the ionic product of water. So let's get on with it. Okay, so the first thing to mention is that pH and the pH scale is a measure of the hydrogen ion concentration in a solution. Now, why do we use pH instead of just hydrogen ion concentration? Well, two reasons really. One is that the numbers that are involved when we're looking at hydrogen ion concentrations are very awkward indeed. They're use standard form and they might be to the minus powers, and they're not very intuitive numbers. And also they can vary enormously. So at very high concentrations, like in acids, then there's going to be a massive difference in hydrogen ion concentrations to strong alkalis. So what the chemists of old decided to do was to express the concentration of hydrogen ions on a log scale. And the log scale looks like this. So the pH is expressed as the minus log to the base 10 of the hydrogen ion concentration, like that. And that's what relates pH to hydrogen ion concentration. So let's look at a little example. Let's say we've got a solution of hydrochloric acid, and it is a 0.01 molar concentration, so 0.01 molar, and molar is the American term for moles per decimeter cubed, so that is the concentration of the hydrochloric acid. So it's the same as saying 0.01 mole per decimeters cubed. So we have the concentration and we want to know the pH. So we fit that concentration into the equation above to give minus log 10 of 0.01. And when you feed that into your calculator, you're going to find that it comes out at 2. I've listed the pH to 2 decimal places because at A level that is the accuracy that you'll usually be required to express your pH values to. Just a reminder on the pH scale, you'll remember that the pH scale goes from about 0, and I've written that in red, so you get strong acids at the top end, and then in the middle we're going to have more neutral compounds, so we'll have about 7 in the middle, and then at the alkali end it goes up to about 14, and they are deep purple coloured. And that's a quick reminder of the pH scale, with pure water being about pH 7 at 25 degrees C. Let's just put some examples down with some strong acids. We're going to have hydrochloric acid and sulfuric acid, nitric acid at this end of the scale, and then strong bases at the other side of the scale might be sodium hydroxide and potassium hydroxide, and in the middle here got pure water. So next, let's do the reverse. Let's calculate the hydrogen ion concentration from the pH. So we'll start off with the equation that we had before. If you remember, pH equals the minus log to the base 10 of the hydrogen ion concentration. And those mathematicians amongst you will know that the inverse of that equation is the hydrogen ion concentration. Right, it's going to be 10 because it was log to the base 10 of the minus pH. So let's do a little example here. Let's say we have a solution of sulfuric acid, and it's got a pH of, I'll write down sulfuric acid to remind ourselves, and it has a pH of, let's call it 1.52. And what we want to know is the hydrogen ion concentration. So I'll write that like this. Hydrogen ion concentration is what? So the way that we can do that is we can use our equation that we've just worked out, the inverse of the pH equation. So the hydrogen ion concentration is going to be 10 to the power of the minus pH, which is 10 to the minus 1.52. We feed that into our calculator, and that's going to come out at 0.030 mole per decimeters cubed. And the alternative way of writing that is to just write it as 3.0 times 10 to the minus 2 moles per decimeter cubed. So what I'd like to do next is to introduce a new term to you, to some of you at least, and it's this term monoprotic. So monoprotic means you get one proton for every acid molecule, and examples would be hydrochloric acid. So for every molecule of hydrochloric acid, you're going to get one proton and one chloride ion when they dissociate in water. And another example might be nitric acid. So nitric acid, HNO3, when that dissolves, that fully dissociates into one proton and also one nitrate ion. So you can see in both cases that's a one-to-one relationship of hydrogen ions to the acid molecules, where these are the acid molecules, of course, in either case. So let's do a couple of examples. Let's use nitric acid, for example, and let's say we have nitric acid where the concentration is 0.05 molar or moles per decimeters cubed, and we want to calculate the pH. Okay, so we're going to use the log version of the pH equation, which is, if you remember, pH equals minus log to the base 10 of the hydrogen ion concentration. Now, what is the hydrogen ion concentration? What is that? The concentration that we've been given, 0.05, is the concentration of the nitric acid. However, it's a monoprotic acid, and we have a one-to-one relationship of hydrogen ions or protons to the acid molecules. So we can say that the hydrogen ion concentration is also 0.050 moles per decimeters cubed. So the pH of the nitric acid is minus log to the base 10 of 0.05. And when we feed that into our calculator, we come out with an answer of 1.30 is the pH. All good so far. Let's do the other calculation. Let's go back to hydrochloric acid, and let's say we have some hydrochloric acid that has a pH of let's say 2.45, so quite dilute. pH of 2.5, and we want to know what the concentration of hydrochloric acid is. We want to know the concentration of hydrochloric acid. So in this case, we want to use the inverse of the pH equation. So we're going to write down that the concentration of hydrochloric acid, in the same way as in the blue example, is the same as the hydrogen ion concentration because of the one-to-one relationship with monoprotic strong acids. And so that is going to be 10 to the minus pH using the inverse equation. So let's just feed in our pH, which we've been given in the question as 2.45, and then we put that little sum into the calculator, and that's going to come out at 3.55 times 10 to the minus 3. Let's not forget the units, moles per decimeter cubed. Done. So if monoprotic means 1 proton per molecule of acid, diprotic surely means 2 protons per 1 molecule of acid, and surely it does. So an example of a diprotic acid would be sulfuric acid, which you know is written as H2SO4, and when that dissociates, when it's a liquid, and then dissociates into water, you're going to get 2 protons. And of course a sulfate ion as well. So you get 2 protons for every 1 molecule of sulfuric acid. So let's look at that example. So let's calculate the pH of 0.1 molar sulfuric acid. So we've got sulfuric acid, we've got 0.100 moles per decimeters cubed as our concentration, and we want to calculate the pH. So if we want to calculate the pH, we're going to use the log version of the equation, and if you remember, that's minus log 10 of the hydrogen ion concentration. But what is the hydrogen ion concentration? That is the first little question to ask. So if our concentration of sulfuric acid is 0.1 and we get 2 protons per mole of per molecule of sulfuric acid, we're going to have a concentration of hydrogen ions as 0.200. And so we're going to feed that back into our equation. So it's minus log 10 of 0.2. Don't need the square brackets. Minus log 10 of 0.2. And when you feed that into your calculator, it's going to tell you that you're going to have a pH of 0.70. And for the sake of completeness, let's do the alternative. Let's do another calculation now. So we're going to calculate the pH of 0.25 molar sulfuric acid. So in this case, so if the concentration of sulfuric acid, let's put H2SO4, concentration, if we're given that to be 0.25 moles per decimeters cubed, then what is the pH? Let's write that up here so we remember what the question is. What is the pH of that? So the first thing to do is to work out what the hydrogen ion concentration is. Alright, so the hydrogen ion concentration again is going to be 2 times the acid concentration. So that's going to be 2 times 0.25, and that of course is 0.50 moles per decimeter cubed. So then we're going to feed that into the equation again, pH equals minus log 10 of the hydrogen ion concentration, which is 0.5, so I put the square brackets there, and feeding that into your calculator you get 0.30 as the pH of that concentration of sulfuric acid. So now we're going to deal with the pH of strong bases instead of acids, and this is slightly more difficult than the pH of strong acids in that bases are donating hydroxide ions. So just to start off with, let's remind ourselves a couple of examples of strong bases. Sodium hydroxide and potassium hydroxide would be 2 examples, and they would both fully dissociate into sodium ions in this case, and hydroxide ions, and potassium ions and hydroxide ions in the case of potassium hydroxide. And what you notice straight away is that in both of these cases, for every 1 molecule of sodium hydroxide, you get 1 hydroxide ion, and the same for potassium hydroxide. For every 1 potassium hydroxide, let's call it a repeating unit, you get 1 hydroxide ion. In the same way, you can say that if you had a concentration of potassium hydroxide as 0.02 mole per decimeters cubed, you're going to have a concentration of 0.02 mole per decimeter cubed of hydroxide ions. But we're going to want to calculate the pH, and the pH, as you remember, is calculated from hydrogen ion concentrations. So the little extra step that's involved in calculating the pH of strong bases involves the use of the ionic product of water, if you remember. Okay, so let's just remind ourselves what the ionic product of water formula is. So we've got the ionic product of water is the concentration of hydrogen ions times the concentration of hydroxide ions. And so if we are given the ionic product of water and we can work out the hydroxide ion concentration, then we can work out from that the hydrogen ion concentration. So just to repeat that, this might be worked out from a question. This might be given, and in which case we would work out from this formula here, the ionic product formula, we would work out the hydrogen ion concentration and feed that into the pH equation. So let's have a look at an example. So let's say we have some sodium hydroxide. So we have some sodium hydroxide, and we're given the concentration. So let's write that in square brackets then, the concentration of the sodium hydroxide, let's say we're given that as 0.1 moles per decimeters cubed at a certain temperature. Let's call that 298 Kelvin. And then the value of K, the ionic product of water at 298 Kelvin. We're reminded that that is 1.0 times 10 to the minus 14, and the units for that would be mole squared, dm to the minus 6. And what we're required to do is to work out the pH of the sodium hydroxide. That's what we want to do. So first of all, we want to find out the hydrogen ion concentrations. So we're going to take the ionic product. Alright, we're going to rearrange that, and that's going to be hydrogen ion concentration equals the ionic product value divided by the OH minus concentration. And in this case, we've got the ionic product as 1.0 times 10 to the minus 14, and we've got the hydrogen ion concentration as 0.100. So we feed that into our calculator, and of course, well, we don't even need to feed that into our calculator because that's coming out at 1.0 times 10 to the minus 13 moles per decimeters cubed. So now we have the hydrogen ion concentration, and so it's an easy process to, I'll just work over on the left hand side here, to get out our log version of the pH equation. So let's just remember it. pH equals minus log 10 of the hydrogen ion concentration. Substitute in the hydrogen ion concentration. That was 1 times 10 to the minus 13. And so that gives us a pH of 13.00. That is the pH of the sodium hydroxide. Okay, finally, let's just review our learning objectives. First one was that we wanted to know that the pH is equal to the minus log 10 of the hydrogen ion concentration, and I think we know that now. We've practiced it as well. And then we're going to convert concentration into pH and vice versa. So in order to do that, we need the other version of the equation. Okay, the inverse of the pH equation is the hydrogen ion concentration, and so now we can go either from concentration to pH or vice versa. And then we had a look at strong acids, and we looked at both monoprotic and diprotic acids, and we worked out that the concentration of the diprotic acids led to a double concentration of hydrogen ions, whereas a monoprotic acid, the concentration of the hydrogen ions is the same as the concentration of the acid. And lastly, we looked at calculating the pH of a strong base from its concentration. And the little complicating factor that we looked at there was the use of the ionic product equation in order to convert hydroxide ion concentrations into hydrogen ion concentrations, which we could then use to work out the pH. Yeah, all done.